Okay, now we are talking about rational functions. Just kind of quick recap of yesterday, maybe. These are things that look like fractions that are made of polynomials. Right, rational, related to ratio, rational numbers are fractions, rational functions are fractions, where we're talking about a thing that's sort of made of a polynomial on the top and bottom. One of the big important things is that dividing by 0 is bad, right? Thinking just about numbers, like division by 0 is undefined as an operation. Here we're talking about functions that look like, I don't know, something like that, maybe. Because you have a thing that varies in the denominator, right? You have a denominator that takes on many values. It's possible that somewhere that would be 0, right? So for like this one I just wrote, if x equals 2, we have or would have 2 over 0. But again, that's a problem, right? Because division by 0 is undefined. So because of that, like things happen there. In particular, x equals 2 cannot be in the domain of that function because, well, there's no way to evaluate the function there, right? It gives you an undefined operation. So to find the domain of a rational function, we set the denominator equal to 0 and solve. And what you find then is points like that, like 2 and the one that we just talked about, that you have to sort of avoid or that are not in the domain of the function. So let's just look at a quick example. Say y equals 1 over x plus 2 times x minus 3. And I want to find the domain. So to find the domain here, what we would do is take the denominator, x plus 2 times x plus 3, set it equal to 0, and then solve that. Now I gave it to you in factors, except I changed a minus to a plus somewhere. X plus 2 times x minus 3, set it equal to 0. It's in factored form already. So like at this point, we're solving a polynomial. So anything we know about solving polynomials comes into play, factoring, quadratic formula, other stuff. Generally, it's going to be things that, probably that part's not going to be like really like dense and difficult, but it should be something that we can do. Often I'm going to choose stuff that like either factors pretty easily or maybe give it to you factored, or something that's like, maybe like homework, maybe like a fairly straightforward quadratic formula kind of thing. On a test, I don't want that part to be like really difficult though. But set it equal to 0 and solve. This one's already factored. So x plus 2 is 0 or x minus 3 is 0, which means -2 and 3. Those are the zeros of the denominator, right? So what we just figured out is that when x is -2 and when x is, I know I'm leaning over this thing. When x is -2 and when x is 3, you get 1 divided by 0 there, right? Imagine that, or plug them in if you want. If x is -2 here, this term is 0. 0 times anything is 0. So you get 1 over 0 at both of those points. That means that the domain of the function does not include -2 or 3. Everything else is fine because any other X value in the whole wide universe would give you something that's not 0 in the bottom, right? If you want, we can look at this thing real quick. Shoot, +2 minus 3, +2 x minus 3. -2 and 3 were the points that we came up with, right? And look at what happens at those X values. You get these, sort of clean, like vertical breaks in the graph, right? You can imagine, or here I can put it on there, but you can picture a vertical line that sort of fits in there that the graph, again, kind of like hooks into, right? We call those asymptotes. So the domain of this function would be everything except those 2 points. This has vertical asymptotes at x equals -2 and x equals 3. Okay. We all right with that? Any questions about anything so far? All right, let me throw you another one real quick. Do the same thing for, let's see, find the domain for y equals x plus 4 over x plus 1 times x plus 4. See everything. There you go. Okay, so take a minute, think through, doing the same kind of stuff, finding the domain. Graph that also, look at it, see what you see. Finding the domain just means coming up with this. Here, we're actually like, here where I found the vertical asymptotes, we're kind of classifying what happens there, but try to think through that as well. Take a minute, think about that on your own, talk to people around you, and then we'll all talk about it in a minute. Good news, everyone. My wife somehow left her car keys in the car that is sitting out there, and not the one that's at our home. All right, what do you got? All right, so set that equal to 0 and you get what? -1, -4. Now, that means that if x is -1 or if x is -4, you've got 0 in the denominator of the fraction. You're dividing by 0. That's a problem. That can't happen, right? So that means that the domain of this thing is everything except those two values. Anybody graph it? Not yet? Okay. Let's take a look at the graph. What is x plus 4 over x plus 4 times x plus 1. There it is. Okay, so -4 and -1 is what we came up with. I mean, first of all, what do you notice about the graph? This may be different than the last one. I mean, we came up with two places where things happen, right? -4 and -1. At -1, we see that, sort of clean, like vertical break in the thing, right? There's a vertical asymptote there. What about -4? Doesn't look like anything's happening, right? What happens if you try to plug -4 into this thing? You get 0 over 0. Okay, well, we know that dividing by 0 is a problem, right? But is it still a problem if you're dividing 0 by 0? If we think about the equal sharing thing, this is that you have no cookies and no friends. Like a sad state of affairs, but a little bit less weird than maybe, or maybe more weird. I don't know. This is a thing that we call an indeterminate form. This dividing 0 by 0 thing is somehow like less bad than trying to divide 1 by 0. So what happens, another way to look at this is that if you just look at this sort of algebraically, what do you really want to do with that x plus 4? Cancel it, right? I mean, it looks like it ought to cancel. And you can kind of, except for this one spot, it would be the same. So what happens at -4? And Desmos will actually show it to you if you highlight it. Can y'all read that? It says -4 comma undefined. And what happened to the point? It changed from being solid to, why am I looking there to see what it's doing? Changed from being solid to being open, right? So what happens there is that there's a hole in the graph, or sometimes it's called a removable discontinuity. So there's still a discontinuity. There's still a place where the thing is not defined, right? It's still -4 is still not in the domain of the function, but it's not as bad nearby as what happens at -1. So rather than, sort of breaking and turning really steep and getting that vertical asymptote there, you just get this single deleted point. It's like you drew the graph, but then just erased that one spot that we call, again, a hole or a removable discontinuity. We're not going to see that come up a lot, but I want you to be aware of it. So this has a vertical asymptote at x equals -1 and a hole or a removable discontinuity. That's the fancy math word if you want to impress your friends at parties, at x equals -4. Oh boy. Okay. Okay. Does anyone have any questions about that? And again, the way that you recognize that is this factor that shows up in top and bottom and looks like it ought to cancel, right? If you do cancel it, you just get the thing that looks just like 1 over x plus 1, like the graph that we just looked at, looks exactly like the graph of 1 over x plus 1, except for that one missing point, right? That one spot in the graph that's not there. Okay, so that's how the like continuity and domain and vertical asymptotes and holes stuff all works. That's all tied to what happens when the denominator is 0. The other sort of big question here is, what about the in behavior thing, right? Think back to stuff we looked at yesterday. The other big thing that we talked about was this idea of the horizontal asymptotes. Now, horizontal asymptotes kind of exist for a different reason. Like vertical asymptotes happen at places where you would divide by 0 in a way that causes the thing to sort of like, go out of control nearby, where you've got, something that's like 1 over 0 or dividing a number by 0. Horizontal asymptotes, so because of that, you can't cross those, right? Because how functions work, vertical asymptotes are like a brick wall, like they're a hard barrier, nothing crosses those. You just sort of skip over them. Horizontal asymptotes, though, those really tell us about what the ends are doing. You can have stuff that crosses over those, somewhere kind of in the like middle, right? But what they really do is tell you about what the end behavior does. So like when we've talked about end behavior over the last couple of weeks, it's been stuff like, well, the ends go like that, and I know because of the degree and like whatever else, right? Now the answer to what's the end behavior look like might be, up and down or whatever, or it might just be that they're like level, right? They're sort of going out like horizontal to the left and right. And if that's the case, then we need to also say like where, right? So here the ends are level, right? They're flat basically at y equals 2. Here they're level or flat at y equals 0. That's not where I want to be. So that's kind of the other big piece of this, is describing the end behavior. What did we look at to figure out the end behavior when we were dealing with polynomials over the last couple of weeks? Whether the leading coefficient was positive or negative, and say again. Right. So if you had an equation, right? If you had the equation for the function, what would you look at to tell you what the ends are going to do? The degree, right? Whether the degree was even, in which case they went the same way, or odd, in which case they went opposite ways. It's because the degree is bigger than everything else, right? Or the term that carries the degree, the leading term, it's bigger than everything else eventually. For the end behavior here, we're going to do basically the same thing. We're going to look at the leading terms. So this thing, the same example, it's factored here, but if we expanded it, or at least looked at like what the leading term would be, right? It's 1 over x squared and then some lower order stuff, right? We're interested in the leading term, so I'm not going to worry about the details on the other stuff there. When I say look at the leading terms, well, it's a fraction, so there's 1 on top and there's 1 on bottom, right? So the leading terms here, 1 on top and x squared at the bottom. These lower order terms that I'm not even bothering to figure out what they are exactly right now, when you go out far enough, when X is, big-ish, right? And that could be 10 or it could be a million. When you go out far enough though, the square term, the one that's got the highest power, is so much bigger than all of these that these start to not matter very much, right? If X is 10,000 or something, 10,000 squared is a whole lot bigger than 6, right? So we don't care about the lower order terms. That's the same thing we leaned on in the polynomial stuff. So eventually this is going to look a lot like 1 over X squared. I'll write a little more of that first time. Eventually, so when we go out far enough, this looks like 1 over X squared. Now, if X is big, right? And big, again, can be relative. So just like pick a number, like 100, right? If X is 100 squared is really big then, right? Like 10,000, not that that's super important, but what does 1 divided by a really big number look like? What kind of a thing is 1 divided by a really big number? Very small, right? I don't have to get too far into the details, but it's very small. And the further you go, the bigger the denominator is here, right? Because it's 1 divided, you're taking a fixed thing, dividing it by a thing that could be, as big a number as you want. That's going to be small and getting smaller the further out we go, right? So what that thing's going to do is just get closer and closer to 0. Right. So just like we looked at yesterday when, we pulled up the graph and like went out and zoomed in, all that kind of stuff. There's always kind of a little bit of a gap there. Right. But the further out you go, the closer it gets to 0. Let me just graph that real quick so we can. Just do this 1 over. This is what we're talking about, like out here, right? In behavior, so as we move off the right and the left, like edges of the graph, what do those ends do? Well, if you were just going to describe it by pointing, you'd say they do that, right? They point left and right, and they're like level. And where do they level off? 0, right? The x-axis. So this has a horizontal asymptote. At y equals 0. Okay, make some kind of sense so far? Does anybody have any questions about things? All right, so here's how this thing can go. There are kind of 3 things that can happen, right? We are comparing the leading terms. How do I want to say this? Well, let's just call that the first example, right? I'm just going to describe that as the thing is like bottom heavy, right? Because the degree in the denominator is bigger than the stuff on top, right? Top you got just 1, just a constant. The bottom you got x squared. If there was stuff to reduce there, you would reduce it, but get down to the point you can look at it as something like this. It's bottom heavy because this is bigger than that, right? Eventually. What happens in that case is exactly what we saw here. There's going to be a horizontal asymptote at y equals 0. Because if the denominator is bigger than the numerator, then when x is big enough, it's going to be a lot bigger. So you're going to have a really small number that's going to flatten the whole thing out at 0. Let's call this balanced. So something like that, maybe. What do I mean when I say this is balanced? We're looking at the leading terms, that's those, right? When you go out far enough, so when x is 1,000 or 1,000,000 or whatever, the +1 and the -2, like, kind of who cares anymore, right? So what's another dollar if you're making it 1,000,000 anyway? So those don't really matter so much. So what happens when you go far enough out is that this starts to look pretty much like x over x would look, right? And if you see x over x like that, what do you want to do? Reduce it, right? Cancel to what? 1. So what does that mean about the way this thing behaves far out, you know, the end behavior? There's the graph. How would you describe the ends? Up, down, level? These? Right, not the stuff in the middle. We're talking end behavior, so left and right. Level, right? Flat, horizontal, right? That one goes that way, that one goes that way. Okay, if that's the case, we also need to say where. So where do they level off? Looks like 1, right? Where do we see 1 show up? Right there. So what if this was, what if this had been 3x minus 2 on the bottom? What would that change? Now the leading term is x over 3x. And when you reduce that, what do you get? 1 over 3, right? When you cancel the x's. The behavior, up or down or kind of flat, leveled off. Left and right edges, right? Don't look at the stuff in the middle. Oh my gosh, there's a giant TV with a thing behind you. So don't look at the stuff in the middle. What do those do? Level, right? Flat. Where? It's a little bit hard to tell from the picture, but 1/3. Right? So if they're sort of balanced like that, meaning the degree is the same on the top and bottom, right? Then just sort of peel the leading terms out, right? Separate those off to the side somewhere like this. And then think about like reducing or canceling, right? You can do that here. You can't do it here. You can do it here though, because what we're doing here is trying to figure out what happens far enough out, right? So it's okay that we lose the detail about the middle. What we're interested in is what happens out there. This reduces to 1/3. That's where the horizontal axis is. Okay. Well, so we've looked at when we've got a numerator and denominator, right? It's a fraction. We've looked at what happens if the degree here is bigger. We've looked at what happens if they're the same. The other option would be if it's sort of top heavy. Going to do the same thing though. Separate out the leading terms. Because again, far enough out, the +5 and -1, whatever lower order stuff doesn't matter anymore. So if I just take the leading terms, I get x squared over x. Can we do anything to simplify or cancel or reduce that? What would it be? Just x, right? What does that mean? The other times we got a number, right? Again, don't worry about the stuff in the middle. I'm not gonna hop up here again because I almost killed myself and I imagine this thing's expensive, but how would you describe the end behavior? That one's going up, this one's going down. Okay, so is there a horizontal asymptote? No, because horizontal lines are flat, right? They're level. So there's no horizontal asymptote. There is what we call a slant or oblique asymptote right there. Oh, it's not quite right. Oh, because that's not what, it doesn't matter. There is one there. That's not quite the right one, but you can kind of see what I'm going for. It should be down a little bit further. We're not going to worry about finding those. Again, if you go on to calculus, you'll revisit this problem later. It'll be somebody else's, I mean, like the future version of U's problem. You just divide to find it. But there is a slant or an oblique asymptote there. For the stuff that we're going to do, we would just say like there's no horizontal asymptote, right? Like you can still describe the end behavior by what it's doing. We're not going to worry about finding that specifically, but we could say like there is a slant asymptote. The way you would find it is just dividing. We're just not going to get into that part. Okay. But that would look something like this. Like the thing was, you know, kind of top heavy. It reduces down to something that still has like an X in it like that. This has no horizontal asymptote, has a slant or oblique asymptote. But again, we're not going to worry about finding that. Okay, so does anybody have any questions about anything at this point? A lot of stuff, right? Here's the thing. Take a few minutes. Let's call it 5 minutes. Take 5 minutes. Figure out what you can say about that. And if you want to jump right to graphing it and looking at it that way, that's fine. But see what you can figure out about this thing. Okay, we'll start by figuring out where this thing lives, right? Where it's defined. The way we figure out where it's defined is by looking at where it's undefined. So where do we have, trouble here? What x values are a problem? -3 and 4, right? Set the denominator equal to 0. -3 and 4. That's where we have trouble, right? That's where it's undefined. Those are the 2 and only 2 values that would make the denominator here 0. Everybody okay with that? Okay, so what's the domain then? Everything else is fine, right? You can divide by anything except for 0. Those are the only 2 places that that you would divide by 0. So domain is everything except those. How do you write everything except those? -infinity to -3 union. -3 to 4. Yep, everybody agree? Yeah, perfect. Okay. So it's like you took the whole number line, the whole x-axis, and erased those 2 points. There's like a lot of bird sounds happening outside, right? Okay. Someday last week, I was walking to the nursing building for my 11 o'clock, and there was like the same kind of thing, like too much bird noise, and I couldn't see any birds, and that was spooky for. Like, I don't even have a thing with birds. I know some people, like my sister-in-law, is like terrified of birds. Anyway, it doesn't matter. You okay? That's the domain. Now, at -3 and 4, because of what just happened, right? Because those make the denominator 0, we have discontinuities. So what we want to do is decide like what kind of things they are, right? What happens there? So what happens at -3? Your choices are it's either a vertical asymptote or it's a hole in the graph. Vertical asymptote, why? What would have to happen for it to be a hole? To be able to cancel, right? You'd have a factor that looked like x plus 3 in the top also. We don't, so it's not a hole. Now, of course, you can also look at the graph. -3 is right there. That looks like a place where a vertical asymptote happens. And then 4, same thing, right? So because you don't have that same factor showing up at top and bottom, it's not a hole. That means there are vertical asymptotes, which I'm going to abbreviate, at x equals -3 and x equals 4. Okay, so basically we're just classifying what happens at those 2 points that we already found, right? Just deciding like, well, do I have what it would take for that to sort of reduce out and make just a hole in the graph, or is it going to really break the thing and put in a vertical asymptote? All right, what about the end behavior? And you can do at least part of this from the graph, right? Looking at the left and right edges of the graph where it sort of leaves what we see, is it pointing up, down, or just kind of leveling off? Leveling off, right? That means there's a horizontal asymptote. Then we need to figure out where. So there's a horizontal asymptote, y equals something. How do we figure that out? Look at the leading terms. So if we took this thing, which is factored right now, but if you multiplied everything out, what would the leading terms be? You don't have to actually do it, right? Because we don't need the whole thing. We just need the biggest term, the thing that's got the highest power on it. So what would that be in the top? X squared. And in the bottom? X squared, right? Now, if you want to multiply the whole thing out to, see what it is, like go for it. If that helps you, then I'm not saying don't do that. I'm just saying you don't necessarily have to. The leading term is going to come from where this hits this. which would be x squared. And the bottom where this hits that, which would also be x squared. X squared over x squared would reduce to 1. So what's the horizontal asymptote? Y equals 1. Now, again, that's hard to spot, especially if it's, I don't know, 2/3 or something like that. It's hard to identify that like just visually that that's where that's happening. But looking at the graph should at least give you kind of a way to check. Like, it's sort of a like, well, that looks about right kind of thing. But we've shown from working this out that that's actually where it is, right? Y equals 1. So this is, my 3 like examples before. This is where it's, sort of balanced, where they're the same. Okay, cool. Everybody good? Any questions about anything? Okay, so if I was going to try to sketch this thing, what I would do is start with that. Basically, like use all the stuff we just found to sort of frame it. I'm not really going to have room here. It'll be fine. It'll all be fine. -3, there's a vertical asymptote. 4, there's a vertical asymptote. 1, there's a horizontal asymptote. We could also find intercepts, right? How would you find x-intercepts for this thing? How do you always find x-intercepts? X-intercepts mean where you hit the x-axis, so where y is 0, right? If you let y be 0 there, you're looking at something like that, which looks like a lot, but everything is factored, so it's not so bad. And we already kind of know how to get half of the stuff out of it, right? Can this whole thing, this fraction, don't look at it as a bunch of like scary x's and, complicated looking algebra thing. It's a fraction. You're looking for where a fraction is equal to 0. Can the bottom be 0? No. So where does it have to happen? Top. That looks a whole lot nicer, right? Especially since it's already factored. So what are the x-intercepts? -1 and 2. -1, 2. -1, 2. So all we have to actually do to find that is figure out where the top is 0 because it's a fraction, the denominator can't be 0. How would you find a y-intercept? How do you always find a y-intercept? Plug in 0 for x. 1, -2, 3, -4, -2 over -12, so 1 over 6. Getting the actual like shape of the thing, that part gets a little bit much because you got to figure out like, should it be, above or below or whatever. You can kind of use multiplicity a little bit here, like these both have multiplicity 1, so they should just go straight across. So if we've got those 3 points on the piece in the middle, I know that it's going to kind of look like that, a little bit like a wonky parabola kind of thing. Those outside pieces look like that. Again, I'm just pulling that from the graph that I've already looked at to get the shape. But we looked at this thing and worked out kind of where everything came from. So what we're doing is using all of that polynomial graphing stuff and solving stuff that we spent the last 3 weeks working out. Now we're doing that, just kind of doing it twice, right? For like the top and the bottom. And, you know, there's an added layer kind of to, you know, what things mean, right? What does it mean to find the zeros from the numerator? Those are the x-intercepts. What does it mean to find the zeros from the denominator? Well, those are places where it's not defined, so you get discontinuity. So that tells me about vertical asymptotes and holes. And then the indicator. Okay, well, indicator, we're taking that leading term idea from polynomials and kind of extending it a little bit, right? So, you know, kind of just go into it with that mindset. I know, like, altogether, this looks like a lot, right? And it kind of is, but it's another place where, like, if you know, take the time to sort of work through it and get your head around it, none of the individual things are hard. It's just conceptually that, like, there's a lot of, you know, there's a lot of stuff going on. So there are 3 others there that you can work through the same stuff, and they're smaller, right? There's less going on. But finish those up, 1, 2, and 3 on the notes there. Again, my, you know, filled in copies in Blackboard, so you can look at those. You can graph them to see, you know, to check a lot of the stuff. Thursday, we will start talking about like solving equations and stuff. We'll probably start with, you know, another like graphing type thing, take 10 minutes or something, and, you know, kind of have another one of these that we work through together, or maybe you work through on your own, and then we talk about it all together. But we'll pick up there on Thursday. You should be able to, you know, at least get into and do a good amount of the 5.1 and 5.2 homework now, though. That's all domain and asymptotes and graphing and all that kind of stuff. So I would, you know, finish these, go to the homework, do some stuff, keep track of stuff we want to talk about, and then we'll hit whatever we need to on Thursday. All right. Have a good day. See you Thursday.